Hello, welcome to this lesson of linear algebra. We're going to continue working with solving eigenvalues, and then in subsequent sections we'll work on the eigenvectors. So let's just get some practice. What if your matrix A was 2, 7, 7, 2, very simple 2 by 2 matrix, and you want to find the eigenvalues of this matrix. I've taught you the derivation and kind of how it works, but basically all you need to do is find the determinant of what we call the characteristic matrix, where we put lambdas on the diagonal, like this. Everything stays the same except we put minus lambdas on the diagonal, and then we set it equal to 0. So even if you don't understand the derivation, or if you don't care, this is what you do. And since it's 2 by 2, we go like this: 2 minus lambda, 2 minus lambda, minus 49 is equal to 0, because 7 times 7 is 49. And then we expand this. This is going to give us 4 minus 2 lambda plus lambda squared. This guy gives us lambda squared minus 49, and that's equal to 0. Okay? And so then we just basically simplify. Lambda squared, this is going to give us minus 4 lambda, and then this is going to give us minus 45, and that's equal to 0. So we first try to always factor these things. This is called the characteristic polynomial. You always get that whenever you're trying to find these eigenvalues. Put a lambda here and a lambda here, and 9 times 5 is the thing that comes to mind to make 45. And of course I can say minus and plus. That'll give me a negative 9 lambda. This will give me a positive 5 lambda. That's going to give me what I want in the middle. So basically I'm done. I can say that lambda is 9 when I set this equal to 0, and lambda is equal to negative 5. So 9 and negative 5. These are the two eigenvalues. You basically follow the exact same procedure all the time. You put the minus lambdas on the diagonal, take the determinant. In this case, we're using crisscross. We get down here, we find the eigenvalues. If you can't factor it, then you have to use quadratic formula. Or if you can't even use quadratic formula, like maybe you get a larger degree polynomial down there, then you have to use other methods to find it. Or you could use a calculator to find the eigenvalues. But let's crawl before we can walk. Let's do one more. What if the matrix in question 3, negative 2, 1, negative 1. I want to find the eigenvalues of that, and so I take the determinant of 3 minus lambda, negative 2, 1, negative 1 minus lambda. I just do this guy on the diagonal, set that equal to 0. So I do crisscross, like I always do. 3 minus lambda, negative 1 minus lambda, and then I subtract negative 2. Okay? So let's go ahead and expand this out. 3 times negative 1 is negative 3 plus lambda. That comes from these terms. Minus 3 lambda. And then I have plus 2 is equal to 0. And I forgot one thing. What did I do here? I forgot one thing here. I got this one. I got this one. I have to have plus lambda squared. Then I have plus 2. And that's equal to 0. So that is the... Well, it's not totally simplified yet, so let's wait on that. So lambda squared, this will be minus 2 lambda, and this is going to be minus 1. This is called the characteristic polynomial. So the first thing you always try to do is factor it, see if you can. Lambda, the only thing that's going to give you 1 is 1 and 1. Now, at first you think you're okay, but then there's no way to get this sign. There's no way to get this negative sign. If this were a plus, and this were a plus, then I think you'd probably be okay. But there's no way, I mean, if you put negative, negative or something, then you get the wrong sign here. If you make this positive, then there's no way you get the middle. So you can't factor. Okay, you can't factor. And so because of that, I'm going to go ahead and erase it. And of course you could dump it into a calculator if you're allowed to use that on a test. At this level, you probably are allowed to use it on a test. Or you could use the quadratic formula. I'm going to give you a little bit of a refresher in that if you haven't done it in a while. Lambda, which is what I'm solving for, is negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b, this is already a negative 2, so negative b is positive 2 plus or minus, and under the square root I have b squared, so this is negative 2 squared is 4, minus 4 times a, which is 1, times c, which is negative 1, all over 2a. A is 1, so 2 times a, that's going to give me this. Okay? And then over here, I'll switch colors. I'm going to have 2 plus or minus the square root, what I'm going to have here is 4, and this gives me a positive, and this is going to give me a 4 plus 4 over 2. So what I have is 2 plus minus square root of 8 over 2. And if you remember back from algebra, if you take the square root of 8 and factor it and pull it out of the radical, because 8 is 2 times 2 times 2, and it's a square root, what you end up having is 2 plus or minus 2 times the square root of 2, all over 2. And this looks nice because since it's divided by 2, I can cancel everywhere in the outside. And what I will have is lambda is equal to 1 plus or minus the square root of 2. So notice that there are two eigenvalues here. There are two eigenvalues here. So lambda 1 is 1 plus the square root of 2, and lambda 2 is 1 minus the square root of 2. Those are two distinct eigenvalues. If you were to put this in a calculator, you would probably just get decimals, but it's a lot nicer to keep your radicals around, just kind of shows that you know what you're doing, and you get an exact solution. Any calculator that would give you a decimal for this would be an approximation. So 1 plus the square root of 2, 1 minus the square root of 2. Notice that the number of eigenvalues you get is always going to be the degree of the characteristic polynomial that you have. And the degree of the characteristic polynomial that you have is going to relate to the dimensionality, or how big your matrix is. So as you get to larger and larger matrices, to find the eigenvalues, it gets harder, because this ends up being a second degree polynomial. We can always solve that. But what if you had a fourth degree polynomial or a sixth degree polynomial? You probably have to use a computer for that, which uses an algorithm that it uses to calculate it. Or you can get lucky and try to factor out a common root or something and get a little lucky there. But we're crawling before we can walk. We're doing 2 by 2 matrices. I'm going to show you how to find the eigenvalues of larger matrices in the next section. Let's go work on a 3 by 3 and get that practice right now.